Bismillahirrahmanirrahim. This is chapter 7, according to your textbook, chapter 34, the nature of light and the principle of the ray optics. Right, so talking about lights, now we are entering or embark on another field of physics. According to your text, this is part 5, alright, so where we are going to learn about optics. So the very base in optics actually about lights. Okay, so before we begin the details of the optics, we need to know what is the light. So light is basic to almost all life on earth. For example, plants, okay, convert the energy transferred by the sunlight to chemical energy through photosynthesis. In addition, light is a principal means by which we are able to transmit and receive information to and from objects around us and throughout the universe as well. Okay, the lights coming from the sun, okay, that we receive the energy from it is actually the source of life in this earth. Many phenomena in our daily, everyday life depends on the properties of lights. When you watch TV, you view photo from your computer monitor, or you are surfing the nets by means of your handphone. Okay, many other. Okay, when you are using mirror to look at your image. Right, so first thing first, we are going to take a look on the nature of light itself. Alright, this is the history. We begin with the era of the ancient Greece, and then after that, Ibn al-Haytham, Islamic scholars, and then we have Newton, Huygens, Young, Maxwell, and Stein finally. So all of these scientists already discussed about the nature of the lights. Okay, in brief, okay, the light is considered as particle during the era of ancient Greece, and then some sort of the idea that the light is actually a wave after that, okay, emerge. And then after that, some of the Westerners be able to prove with some experiment that lights can behave as particle as well. So if we go through, okay, many prediction done and many experiment done, actually at the end of the day, the era here that we are living here, okay, we know that light behave as both. It can behave as particle, it also can behave as a wave. The light exhibits both of the particle and wave nature, but only one can be observed at one instance. If behavior of the light as particle, we cannot observe the wave behavior within the light, vice versa. So it depends on the condition and also situation. Okay, for that particular situation, the light can exhibit or behave as a wave. Some other situation, the light can exhibit as particle. So this is even more details about the timeline in optics. Okay, where 400 BC, Aristophanes talking about lens and glass. Okay, Ptolemy, okay, talking about refraction. Okay, and then Euclid, the first to write about reflection and refraction, you see. And Johannes Kepler talk about how the light focuses, how the light focuses light, law of the rectilinear propagation of the light, discover total internal reflection. Okay, and then Wilbert's Snell's law. Okay, Fermat principle of least time, Huygens principle. Okay, Rømer measured the speed of light by observing Jupiter's moon. Isaac Newton, Euler, okay, Thomas Young experiment, Fresnel, okay, Simon Poisson, Leon Fawcett that figure out the speed of the lights, okay, confirm. And then finally J.C. Maxwell, light is actually EM wave. There is no right or wrong. Both of the behavior, whether particle or wave, actually both of it, the nature of lights, the behavior of the lights. It's just that within some condition, the lights behave as particle. Within some condition, the light behave as wave. The ray approximation in ray optics. Okay, the field of ray optics, or sometimes known as geometric optics, involve the study of the propagation of lights on how the light behave lah. Right, the ray optics we assume that light travels in a fixed direction in a straight line as it passes through a uniform medium. Okay, a uniform medium, and changes its direction when it meets the surface of a different medium, or if the optical properties of the medium are non-uniform in either space or time. This will be discussed in detail later. Okay, in our study of ray optics, okay, here for chapter 34 and also in chapter 35, we use what it called the ray approximation. Right, to understand this approximation, okay, let's recall that the ray of a given wave are straight lines perpendicular to the wavefront. The wavefront is this one. This is the ray. The ray approximation, a wave moving through a uniform medium travel in a straight line in the direction of its ray. So this is the wavefront, right? The ray which always point in the direction of the wave propagation, there are straight lines perpendicular to the wavefront. Okay, now if the wave meets a barrier in which there is a opening, okay, it could be, this is the pattern of the opening, or this, the size of the opening. Okay, so if the size, the D is the size of the opening, it much bigger than the wavelength, okay, part of the lights, okay, or the wave going to be stopped or absorbed here, part of it going to travel further or passing through the opening, and nothing happen if the separation or opening distance is way bigger than the wavelength. But then if the size of the opening, the D, is more or less to approximately to the wavelength of the wave, then now, okay, the wave started to be bent after the opening. It spread out after passing through the opening. Okay, whenever the size of the opening is way smaller compared to the wavelength of the wave, okay, what will happen? The opening behave as a point source, emitting spherical wave, completely spherical wave like this. Right. So this effect or process, we call it diffraction. In detail, we're going to learn about this in chapter 37. Alright. The ray approximation here is very good for the study of mirror, lenses, prism, and associated optical instruments such as telescope, cameras, and eyeglasses. Okay, when we study interference, the diffraction part here, okay, and polarization in chapter 36 and 37, we'll need to look more closely at the wave characteristic of lights later on. Okay, so now we move to analysis model. All right, where we have about reflection of lights. Actually, we already introduced the concept of reflection of wave in a discussion of wave on a string in section 17.3 previously. As with wave on a string, when a light travels in one medium, encounters a boundary with another medium, right? Part of the incident light is reflected. For wave of a one-dimensional string, Okay, the reflected wave must necessarily be restricted to the direction along the string. Okay, for light, for light wave free to travel in three-dimensional space, no such restriction applies. Right, that is the difference. And the reflected light wave can be in directions different from the direction of the incident wave. So if you see here, this is the incident wave, and the reflected wave or lights is not the same direction to the incident wave. But if we're talking about string, it's going to be reflected like this. Still remember this one? Okay, this is a fixed boundary. Okay, in the same or opposite direction, within the same dimension. Okay, however, for the light here, okay, it could be indifferent. Okay, that is the different compared to the string. Okay, figure here, we have here, right, figure here, we have A, B, C and D. This is schematic diagram. Okay, this is the physical diagram or real diagram of it. This is the schematic diagram of it. Reflection of light from such a smooth surface called specular reflection. Okay, so for this one, it's specular reflection. If the reflecting surface is rough, non-uniform like this, okay, the surface reflects the rays not as parallel set but in various direction. It could be any depending on the surface. Okay, reflection from any rough surface is known as diffuse reflection. So this kind of, we call it diffuse reflection. A surface behaves as a smooth surface as long as the surface variation are much smaller than the wavelength of the incident light. This is how we define whether the surface is smooth or not, right? Okay, the difference between these two kind of reflection explains why is it, okay, more difficult to see while driving on a rainy day compared to the dry or clear day. This book, okay, we restrict our study to specular reflection only, this one, all right, and use the term of reflection simply. Okay, it means that specular reflection. Now we are going to embark on law of reflection. Consider a light traveling in air and incident at an angle of theta 1, okay, on a flat smooth surface as shown in this figure. Okay, the incident ray and the reflected ray makes an angle of theta 1 and theta 1 prime respectively, where the angle are measured from between the normal line to the ray. From experiment, it can be shown that the angle of the reflection, theta 1 prime, okay, is equals to the angle of the incident. Okay, where we have theta 1 prime equivalent to theta 1. This is what we call it as law of reflections. Right. Example 34.2, the double reflected light ray. Two mirrors make an angle of 120 degree. Right, so we have mirror 1 and mirror 2, right, the angle between them 120 degree. As illustrated, a ray is incident on mirror 1 firstly, right, an angle of 65 degree to the normal. Find the direction of the ray after it's reflected from mirror 2. So if we see here, okay, this is the incident angle for the ray 1 on mirror 1. So reflected angle must be the same according to the law of reflection. So now it's going to hit the second mirror, okay, at theta M2 as the incident angle for a second mirror. Right, so from this triangle, Okay, we know that the sum of the theta within the triangle must be 180 degree. So, and here, since this is a normal line, it must be 90 degree here, right? Okay, so if we have already information of 65 here, must be delta here is equivalent to 25 degree, right? And then since we already know that here is 120 and here is 25, so for this angle, gamma angle here, it must be 35, right? And then again, this is a normal line, so it's 90 degree. So if we have gamma equivalent to 35, now theta M2 must be 55 degree. And based on law of the reflections, theta prime M2 must be the same to the theta M2, must be 55 degree as well. Right, notice that the angle between the incident and reflected rays at mirror M1 is 65 plus 65, 130 degree. Therefore, the angle by which the direction of the light ray changes from its original direction is 180 minus 130, which is 50 degree. Similarly, for the reflection at mirror M2, the change of direction is 70. Therefore, the overall change in direction of the light for two reflection is 50 plus 70, which is equivalent to 120 degree. Interesting. This angle is the same as that between the mirrors. So, if you see here, right? Okay, the angle is the same as the mirror here, 120. Is the overall change in the direction of the light ray always equals to the angle between the mirror? Is that so? This is the general, okay, what I'm talking about just now. Right, which equivalent to, okay, 90 degree plus theta minus 5. Okay, consider this triangle now, right? Okay, we know that alpha plus 2 gamma plus 2 times of 90 minus theta must equivalent to 180 degree, right? So from here, okay, we are going to have alpha equivalent to 2 times parenthesis theta minus gamma, right? Okay, from this figure we notice that overall change in direction of the light ray from its original direction angle is actually beta. Where's the beta? Here, right? Here. Use geometry in figure to solve for beta. Beta is equivalent to 180 degree. 180 degree if we further line of this beta. Okay, it's 180 degree. Okay, so for beta, 180 degree minus alpha, right? Where our alpha is this amount, so substitute here. This is your alpha, right? So from here we may rearrange, and then beta finally equivalent to 360 minus 2 phi. For example, if the phi is 90 degree, we obtain beta will be 180. In that case, the light is reflected straight back to its original. Conclusion just now, that always the same like this, is overall change in the direction of the light ray always equals to the angle between the mirror, cannot be used. Okay, so you have to check by this. So it's going to be like this, and then like this. The light going to be reflected like that. So now, if the angle between two mirrors is 90 degree, as Madam explained just now, the reflected beam returns to the source parallel to its original path, as discussed in the what if example just now. Right, this phenomenon, okay, where the incident ray is being reflected and the reflected ray is parallel to the incident ray. Okay, this kind of phenomenon we call it retroreflection. Right, retroreflection. Okay, for retroreflection we have so many application of it. Okay, you may read in detail for the application of the retroreflection.